everyone, my name is Diogo and like Art said, I'm going to be talking a bit about Haskell today. So for those not familiar with the language, Haskell is a general purpose, statically typed functional programming language. And since I've started learning it, I've come to notice that a lot of the great ideas in Haskell tend to spread out and infect other languages and ecosystems, some of which have already been taught today. So some of these things first appeared in Haskell and took off, others appeared elsewhere, but then just Haskell just helped popularize them. So before I begin, there's going to be some Haskell code in these slides, and the syntax may be very different from other languages that you may be used to. So I'll explain the important bits as we go, but don't focus on trying to understand every little bit of syntax, because that's not really necessary for this. But if you do see something that you'd like me to explain a bit better, please interrupt me. Right, so let's talk about types. So like in all languages, Haskell gives us a bunch of primitive data types out of the box, like int, boolean, string, character, and all that. But at some point, we want to combine these smaller types into bigger ones. So one way of doing that is by pairing them together. So for example, if you want to express that a person is a pair of a string that represents their name and an integer that represents their age. And these are called product types, and most languages have support for something of this sort. So in C you have structs, in C# you have classes if you ignore the methods. Some languages have records, and this is how you define a product type. In Haskell, they say data person, that's a new data type. It has a constructor, also called person, with two fields of type string and int. I can optionally also give these things a name if I want to, but this is only half the story. So with classes and brackets, let's say that a person is a string or an int, a string and an int. It makes sense that there should also be a way of saying that this new data type that I'm defining is a string or an int. And there is a way to do that. They're called sum types. And for example, I can define a new data type called string or int. And I create an instance of that by using one of those two constructors, separated by a vertical bar. So I can use it's a string, and give you a string, or it's an int, and give you an int. And you can use some types to model a lot of things. So for example, a user's login status might be either logged out, in which case we know nothing about it, or it can be logged in which case we know their username and who they're friends with. I can also use this to model arbitrary JSON documents. So JSON document is either the null token, or I can use the JSON bool constructor and give it a boolean, JSON string, JSON number, or a JSON array, which is just a list of other JSON documents. So those square brackets you see there, that's the list type in Haskell. Or it's a JSON object, that's the hash map of string in JSON. So another example. So here's the thing that I really like about Go. So in Go, the language, you don't throw exceptions. The convention is you return an error value and then you just pass these error values around. And I think this is a really good idea because it forces us to think about error scenarios instead of just sweeping them all under the rug. And also because you can look at the type, at the signature of a function and immediately know whether it can go wrong or not. So a function that can go wrong, in Go returns a double of a string and an error. And if the function succeeds, you return a string and a null error. And if it fails, you return a null string and an actual error. But there's nothing preventing me from returning both a string and an error, or even from returning neither of those things. So instead of using a double, in Haskell you could use a sum type to express precisely what we need, and then you'll be able to return only string in case of success or only an error in case of failure. And when you have a language that lets you freely combine products and sums, you say that you have something called algebraic data types. And because products and sums complement each other, if they're both so fundamental, you think that every language should have these. I don't think it makes a lot of sense to have one, but not the other. But for a long time, most if not all mainstream languages have supported only product types. But luckily that's changing, and a lot of languages took a page from Haskell's book, and now you have algebraic data types in Scala, Kotlin, Rust, and Swift, and TypeScript. They all call it slightly different names, but it's essentially the same thing. And So for example, Java doesn't have any support for this, but there is a library that you can sprinkle some annotations and it'll generate all the boilerplates and make it seem like you do have algebraic elements in Java. Right, so that's one thing. So let's talk about parsing. So say there's a string you have to parse and it follows some kind of pattern, and I ask you to parse that string and extract the basic information from it. So the first thing many people will think of is, well, use regular expressions. Anyone here of final projects? I'm not, sorry. So let's not talk about regular expressions. Let's talk about an alternative called parsing combinators. So in Haskell, there's this really famous library called parsec. And the parsec library gives us a ton of primitive parsers. And so for example, I can use a parser that matches on the string hello, a parser that matches on the character A parser that matches on any character at all, and it'll also extract it so I can use it later. And it also gives us a ton of combinators that we can use to glue all those little parsers together into bigger ones, more useful ones. So for example, we may use the OR combinator. It's not its name, but let's call it that. To say that I want to match on the string hello or on the string world. I can also use Haskell's do notation to compose a sequence of parsers together. So here in the do block, I just create a new parser that will execute those other three parsers in sequence. And it'll succeed if all three succeed, or it'll fail if any of those fail. I can also use left arrows inside the do block to say when that sequence of parsers is run, and only if they're all successful, I want to use the data that they've captured, and I'm going to do something with it. In this case, I'm just putting both of those digits in a tuple. So let's see how this works in practice. So say I want to parse a string that begins and ends with a square bracket and contains a comma-separated list of words. I can start by defining a parser for a simple word, which is simply just the letter parser repeated one or many times. And then I want those words to be separated by the comma character, and I want all of that to be surrounded by square brackets. And that's it. It's as simple as that. What if you want to parse something way more complex, like a raw JSON string into one of those things that we defined earlier? I can do that as well. This slide is a bit heavy, but the basic idea here is if a piece of JSON can be one of 6 things, I'll just define 6 different parsers, one for each thing. So I'll look for the no reserved keyword. I can also look for the true keyword, or if that fails, I'll try the false. I can look for a string literal, that's going to be a JSON string, or a sign and an optional sign and a floating point number. My JArray is just going to be a comma-separated list of JSON values surrounded by brackets, and my object is just going to be a comma-separated list of key-value pairs separated by braces. And what's a key-value pair? Well, it's just a sequence of a string literal, a colon, and a JSON value. And then my overall parser is just a choice between any of those 6 things. As long as one of those 6 succeed, then we're good. Note that I didn't have to worry about handling any white space or escaped quotes inside string literals or Unicode characters or anything like that. It's really that simple. And there you go. It's a JSON parser that fits in a slide, written in 30 minutes or less. And the point I'm trying to make here is that you can use a bunch of those little reusable parsers off the shelf and then just combine them freely like Lego bricks almost. And on top of that, I get some pretty cool error messages for free, because when I compose parsers together, their error messages also get automatically composed into better error messages. And so parser combinators are so easy to reuse and compose that this parsec library has been ported to virtually every mainstream language that you can think of. So next time you need to parse something like command line arguments or whatever, just first check whether there's a parsec combinators library for your language of choice. just name a few. There's an F#, C#, Go, JavaScript, Java, and everyone. Quick check. So James already talked about this, so I'll keep it brief. Right, so say I'm writing a sort function, as you do for an interview, because why else would you write a sort function? Bear with me. And I want to write some tests to make sure that it works. So I can start with this, right? 3 to 1, should give me 1 to 3. But that doesn't guarantee that my sort function works at all, right? It will be just reversing the input list. So I'll write some more tests. So how confident are you that my sort function works with just these 5 tests? Should I keep going? Should I, how many tests are enough? Will they ever be enough? So the main problem here, as James pointed out again, is we're testing for specific inputs, and we're not considering other inputs. So we need to take a step back and ask what exactly are we testing here? What does it mean to sort the list? And it just so happens that sorted list is simply a permutation of the original list, where every element happens to be greater than or equal to the next. So instead of testing for inputs, we'll test for these properties. And quick check lets us do exactly that. We can just write plain old functions. So here's the function that takes a list of ints and returns a boolean, and it just says for any list that you give me, any list at all, if I sort it, I should have a permutation of the original list. And I'll write another property that says for any list that you give me, when I sort it, it should be an increasing order. And then I just ask quick check to verify these 2 properties for me. That's it. And quick check will try to feed these functions lots of random inputs. It will try its best to falsify these properties and find a counterexample. And if it can't, if these 2 properties hold, we can be pretty sure that our function works. And that's it. We fully specified what it means to sort a list, and no need for any unit tests at all. In practice, though, you'll end up writing a mixture of property tests and unit tests. What I personally do is try to encode as much as possible in types, and then write property-based tests for the other things that I can't type, and then I'll fill in the gaps with unit tests. This method of testing came to be known as property-based testing, and I think it's great for 2 reasons. So first, because essentially it's generating a lot of tests for me, so it catches a lot of weird edge cases that I never dream of testing for. And second, because it forces you to think about your system from a much higher perspective, and it forces you to think about properties and which laws govern your system. So one final example. So if we go back to our JSON data type, we have a parse function. You can imagine that we'll also have a render function that sends that JSON value back to a raw string. So one thing we could test for is whether parse is the inverse of render. That is, if we have a JSON object and we render it and we parse it, we should have the thing that we started with. And this is incredibly useful because we want to make sure that our encoders and decoders are consistent. And does it scale? Yes. I mean, you don't have to write property-based tests at unit level. You can use them to verify your client's requirements. You can write it at any level of your system. And again, this technique became so popular that implementations of quick checks started popping up everywhere. There's an F#, there's FS-check, Scala, Swift, Rust, Java is at least 2 competing libraries. Python's hypothesis is really famous, and JavaScript has very funny. Do notation. So we've already seen this today. We've already used do notation to compose a sequence of parsers together. But it turns out that do notation is so much more universal than that. We can use it to combine a sequence of lots of other things. So, for example, a sequence of random data generators, a sequence of async operations like your indexes, your tasks and features. You can use it to combine database queries, collections, nullable values, all that. And some languages have already adopted this method of composition. So there's 3 that I know of. Scala has 4 comprehensions, F# computation expressions, and C# has link. So I think C# is my favorite out of these ones. Any C# in the room? A few, yeah, good. I used to write a lot of C# as well. So C#'s version of the notation is my favorite because it's really well designed. So most people, when they learn C# and come across LINQ, they assume that it's a funny little language for combining lists and other collections together, and that's it. It seems useful, but that's it. When in fact, LINQ is so much more than that. Everything I said you can do with Haskell's notation, you can also do with LINQ. So here I'm just using LINQ to combine parsers and also validation functions. A little side note here, so the effort to add LINQ to C# was led by Eric Mayer, also known for his very colorful t-shirts. And interestingly, he was also a member of the Haskell committee, so he basically managed to infiltrate the ranks and infect C#. So this is something, another example here, the base library. So this is something I've never seen before. So Haskell's base library is so rich, so full of really generic abstractions that these abstractions start to get important to other languages in the form of libraries. And these abstractions, over time, they became like a standard toolkit for doing functional programming. So if you're doing FP in any of these languages, there's a good chance that you're using one of these libraries. And the others, so for example, in Scala, you have two big competing libraries called Cats and Scala Z. The authors of Scala Z, for some inexplicable reason, insist that it's called Scala Z. There's a bunch of other things that I don't have time to go into, like more advanced type system features that have been adopted by mainly Scala, Rust, Kotlin, and Swift. And finally, I think the most compelling piece of evidence for Haskell's proliferation is all the languages that were born from it. So nowadays you can use IDA to write Haskell on the JVM, and it has great interoperability with Java, so you can use a lot of the existing stuff. And they're also working on adding Android support at the moment, so I think the future is very bright there. If you're into front end, you can use either Elm or PureScript. So Elm is like a simpler version of Haskell that compiles down to JavaScript, and it's really well known for being an extremely safe language for front end. And also, it's very beginner friendly, so if you like doing front end, Elm is probably a good place to start. There's also PureScript, which also compiles down to JavaScript, but it's capable of running on Node, so we can write PureScript on the backend as well. And finally, DAL, it's the illustration for Fanning, and it's a programmable configuration language, so you can think of it as like JSON with types and functions on top. So, my 2019 challenge to you is this. So if Haskell is such a fertile ground for innovation and awesome ideas, why not just cut out the middleman and get them straight from the source? Why wait? Why get them second hand? So I personally think there's never been a better time to learn Haskell than today. There's a lot of awesome resources out there. So if you decide to do it, the Haskell book is probably the best place to start. I don't recommend learning Haskell by just piecing a bunch of blog posts together. So my recommendation is just get the book. And if you're a student, or for whatever reason you can afford it, you can contact the authors, and they'll work out discounts. I've also heard really good things about get programming with Haskell, and there's an online course at haskell.com, and they also do discounts. The easiest way to get started is just get a tool called Stack. And if you have any questions at all, there's an FB Slack with an awesome community of people from all over the world eager to just give you a hand. And there's also a local FB meetup here in Belfast. I think one of the organizers is here today, Stevie Olsworth, so just go bother him. And finally, if there's anything I can help you with, you can find me on Twitter or just talk to me after. That's all I have. Thanks for listening.
I think that was very sensible and inspiring talk about Haskell, with the possible exception of the dangerous nonsense about C#. But apart from that, very good. Questions? Yes?
Just a basic comment, Dave. I love your slides.
Thanks.
Say that with the Learning Haskell for a Great Good or whatever book.
Yes.
I was working through that slowly, and that's another good one as well, and it's free and online. So that's another good resource. Yeah. Cool. Questions?
So, very good question, thanks.
So the question was, how long did it take to get proficient with Haskell?
Yes, so I personally, I took the slow routes, so it took me quite some time out of the class, because this book didn't exist back then. So I, unfortunately, pieced a lot of things together to make some sense out of it, so it took me a long time. But I've read reports about a lot of people that took the fast routes, and it takes like a couple of months maybe to get started. To get really proficient, it's some more time, but I think a lot of Haskell usually gets a lot of criticism for having a really high bar for entry. But personally, I think that you don't need to learn how to start using Haskell. It's just that there's a really high ceiling, so there's not a limit to what you can learn in Haskell, and that makes it seem like it's hard, but you don't need to know it all.